Welcome back to another Leetcode problem solving session. Today we are going to be attempting the problem find the punishment number of an integer. It's a medium weighted question, so you can see. So the question says that given a positive integer n, we should return the punishment number of n. So what is the punishment number of n? This is defined as the sum of the squares of all integers I, such that I is between 1 and n, inclusive. And then the decimal representation of I times I can be partitioned into contiguous substrings such that the sum of the integer values of the substrings equals I. Yeah, so there's a lot of English going on. So let's just break down what it actually means. Yeah. So if you take a look at this example now, so when we say the punishment number for n, in this case n is 10. So determining the punishment number for n, 10, means that we're going to go through numbers from 1 all the way to 10. All right, so if you take a look at this, yeah, so the first condition here says go from 1 all the way to n. So we're going to go from 1 all the way to n. So that's 1 all the way to 10. Then we are now going to, for all those numbers, we're going to do the number times the number itself. So basically, we're going to square the number by 2. And once we do that, we then partition it into contiguous substrings such that the sum of the integer values of the substrings equals I. So once you square the number, you have obviously a decimal number. So each of those digits within the decimal number, we need to sort of create substrings out of those string representation of that number, and then sum up all of these substrings together. If it is possible for us to form, or if this sum at the end of the day can equal the value of I, then we can say that the number is a valid combination, and that can be added. So the sum of all the numbers between 1 and 10 is going to be our output. That will be the punishment number. So if we take an example now, look at this explanation. It says here that exactly 3 integers are in the range. Exactly 3 integers are in the range from 1 to 10. That satisfies this condition. And what are those integers? The first is 1. Yeah, so we see that 1 times 1 is 1. The next is 9. 9 times 9 is 81. 81 can be split into 8 and 1, such that when we add 8 plus 1 together, it gives us 9. Do we see? So same thing for 10. 10 times 10 is I times I, that's 100. 100 can be split into 10 and 0, which when we sum together will give us back the same I. So that is the idea of the question, and that is what we're supposed to do. So the second example here is the same. So we're going to find all the numbers from 1 all the way to 37, which when we square it and then we try to sum up each individual, and we try to create substrings out of that square. Those substrings should sum up to the original I. Yeah, so that's basically it, and we could just try to do that. And actually, I think we should do that. So let's just do that. Let's quickly do that in a minute. So the first thing we do is we take the number n. Then we're going to loop through from 1 all the way to n with both range inclusive. Yeah, so we're going to loop through all that way. Then once we loop through, then we are going to determine, so we're going to, let's say we call this looping. At every point we call it I. While looping through, we are going to perform the operation of I times I. Once you perform the operation of I times I, we call it squared. So once we have this, we check if substring, the substring equals I. you check if sum of all substrings, yes, equals I. So we have this check that we perform for within this loop, and then if this is the case, if the sum equals, what we then do is, we have like a accumulating sum that would add the squared value to. So basically we need to sum up all the square values that evaluate to this solution, right? So at the end of the day, we need to sum up the squared. Yeah, so basically this is what we're going to be doing. And if you look at it properly, it's obvious that we're going to look through this integer range for the first time. Then we are going to perform this operation, which is constant. However, this particular check, this process here, could be costly, right? So we need to figure out a reasonable way to approach this side. So let's just begin implementation, and then along the way we're going to work our way through that, right? So we could just say define a sum, call it 0. Remember that sum will be what to accumulate our values. We're going to loop from I is equal to 1, I is less than or equal to n, and I plus plus. Then what do? We define a squared. Squared is going to be I times I. Then I'm going to now check if some, basically let me just copy this. So we're going to just, we're going to perform this operation. We're going to check if this, for the value of so we're passing in squared, and then we're passing in the value of so you check if the substring equals, yeah. So we do this, yeah. So let's just do it like this. So we have, basically this is like a sub problem. So we have the squared, and we're going to figure out if we can, if you can split this squared into some particular substring such that the sum is going to equal to this value. Yeah, so this is what we're going to have. And then if this is the case, then we do a sum plus equal squared. Yeah, so basically this is what we are solving. So the only problem now, or the only part of this problem that we need to attempt, is this part, checking if the sum of all the substrings equals I. So for that, we could create a method that helps us solve the problem. So we just create a private method. We are going to return back a boolean. It's going to be called check if substrings equals this. It's going to take an integer that will be called squared, and then we are going to return a boolean. Yeah, so let's see, let's now take a minute to think about how we can address, or we can solve this problem. So now, assuming that we have a squared, right? So in this case here, where we have 1, you can see that 1 equals, basically this 1 is a squared, equals the original number. Oh, okay, so actually I need both the original number and the squared, right? I need to be able to say that sum of all the digits within the original number gives within the squared number, or sum of all the substring within the squared number equals the original number. Yeah, so I need to actually pass in the original number, so we could just pass in I. Yeah, so squared and none. Yeah, that's I think that's clear enough. So now what do we now do? Yeah, so we now need to figure out, is there a way for us to split out this squared number and get out the such that when we sum it together it gives us num. Yeah. So let's take a minute to think about this. So if we look at the example of 9, so what we do is we say 9 times 9, and then we say this gives us 81. Then we go through each of this, so we sort of like split, create substrings, and then try to split, and then sum. So we could attempt that actually, and what we can do is we can we can split, hypothetically speaking, yeah, we can split out this squared number into its individual digits, get out the individual digits and sum them together and see if they give us 9. And in this case, that would work. Since we just need to split it's an 81 into 8 and 1, sum it together, and that gives us 9. So in this case, we can return true immediately. But in the case where we have 10 and 10, this doesn't entirely work, right? Because if we split out 100 into 1, 0, and 0, and we sum all of that together, we are going to end up getting 1. And 1 does not equal 10. However, if we split out 100 into 10 and 0, we can sum those two parts together and get 10. Yes? So let's take another example. Let's look at this example of 36. So in this case, 36 squared gives us 1296. One thing we can do is, attempt to split them to the individual digits. So we have 1, we have 2, we have 9, we have 6. If we sum all of that together, 1296 will give us 18. That's not equal to 16. That's not what we're looking for. That doesn't work. Okay, so what if we split, we get out 1, then we get out, so let's say if we get out 1, then we get out 26, then we get out 6. Does this work? Yeah, so this works. So 129 and 26, this works. Sum of all of this will give us 36. So this is one valid way. Yeah, so if there is a valid way to split this squared into this kind of substrings, immediately we say that okay, this is a valid number, we return true. Yes. So one more thing we should think about is, trying to come up with this kind of solution or a kind of pattern to this, to be able to, is there a fast way for us to determine if 36 is a valid number? Imagine like for some arbitrary number, is there a fast way for us to determine if there is a way to perform this operation? Yeah, so, and as it turns out, we've seen that if we split the number into individual digits, it's not always going to be correct. So that's not correct. Same way if we split the number into 2 digits. Say for example we split 1296 into 12 and 96. And in this case, this is also not going to be correct. Yeah, so this will give us I think this is 108. Yes, and that is not obviously 96, so this will not work. So that means that the way we divide the number, actually we cannot really say, right? So we sort of like need to check all possible divisions of this number to determine which one of them will give us what we are looking for. This is another division. We have 1, 2, and 96. This will give us 99. It doesn't work. So sort of like we need to check, also 1 and 296 is another division. This also doesn't work. And in fact, we can see that whenever we have a subdivision that is, more than the number of digits within the original number, there is really no point of checking that. That is not going to be possible, right? So this 1 and 296 is pointless. Don't need to check. So definitely going to be false. Same thing for 129 and 96. But to figure out how to divide, we need to exhaustively search. So we need to create all possible forms of substring to find this. And that is a really popular problem. If you think about it, creating all possible substrings from a string is basically all possible substring from a string is basically that's an n-squared problem, because we just need to take an arbitrary value for I and then take an arbitrary value for j. That's always going to be after I, and then for all of them pick an I and pick a j, and then create a substring from that. That is creating all possible substrings, but that is not even a problem. This problem is about checking if the sum of all possible substrings, that is, we need to split. So for every substring that we get, say for example we create this substring for I and j. Okay, this is smaller. Let's say we get this substring for I and j. we cannot automatically take the last bit. We also need to split 9 and 6, 96 into another set of substrings, which could be, it could be 9 and then could be 6. And in our original example, when we had this original full string, we first of all splitted it into one that had 1 and 296. Then we did another split for 29 and 6. So the complexity actually is not going to be n squared. It's going to be much more than that. So what that basically means is that if you take a look at what we did now, it just means that for every index, we kind of like need to decide if we need to split at that index or not. So for example, the first index, we decide, do we need to split at this index or not? If we do decide to split, we have this option. If we do not split, we have our original string the way it is, this way. Then for every one of them, we then need to make another set of decisions. Do we need to split or not split? So in this case, we can decide and say, all right, we are going to split, right? Okay, actually, you know what? Maybe I should just, let me move all of this to a different screen so that it's easy to paint the picture. So let's say that we have, yes, so assuming that we have this. Yeah, so let's quickly just take a moment to look at this. All right, so if we, if we look at the original number now, so this is 1296, so we are trying to split out 1, 2, 9 and 6. So we can choose either to split at the first index or we split at the second index. So we can either end up with 1 with 296, or we just have the 296. Remember, this is the first index. Now, so now for the second index, we can do the same thing. We can either choose to split, in which case we have 1, we have 2, we have 9 and 6, or we don't split that index and then we end up with 1, then 2, 9 and 6. For this, if we split at the second index, we have a 1, 2, 9 and 6. If we do not split, we have a 1, 2, 9, 6. So now if we take the next one, we are now going to be at the third index. So we are at the third index. So at the level of at the third index, we have so let's say, so this will be our third. So at the third index, we can also do the same thing. We can choose to split, in which case we have 1, 2, we have 9, and we have 6. Or we do not split, in which case we have 1, 2, we have 1, 2, we have 9 and 6. For this, if we split at the third index, we have a 1, 2, 9, and then we have 6. And if we do not split, what do we have? We have 1, 2, 9, 6. Yeah, so we can, so for these two, we can, for the third index, we can split or not split. So if we split, we have 1, 2, we have 9, and we have 6. And if we do not split, we end up with 1, 2, 9 and 6. For this, if we split at that index, we have 1, 2, 9 and 6. If we do not, we end up with 1, 2, 9, 6. So now for the final index is going to be our fourth index. And at the fourth index, we can, okay, so there's only 1 digit here. So once we get to this point, we can just return, or we can actually just go ahead to do the evaluation. For that fourth index, I mean, basically the only option there is to just take it. Actually, we can stop at this position, because the division here is just we can only have a 1, 2, 9, and 6 from here. There's no other value we can have. So here we'll end up with a 1, 2, and 96. Here we'll end up with a 1, 29, and 6. And here we'll end up with 12 and 96. I mean, you get the idea. You guys get the idea. So if we attempt to sum all of these individual values, so 1 plus 2 plus 9 plus 6 gives us 18. Then 1 plus 2 plus 16, 1 plus 2 plus 96, which is 9, gives us 99. 1 plus 29 plus 6, which is this, gives us 36. And then for this one, so I mean, remember what we said earlier, that in fact, when we have a division such that the number of digits is already more than the original number we have, we can immediately cancel this. So we can take this number and say, oh no, this is just not going to be possible. So I need to check. And in fact, we can do the same thing for this. Don't need to check. And then for the one that comes next, there's no need to check. So we need to explore this at all. And in fact, we could have actually stopped at this point when we say we will not divide here. There's no need to explore all of this. So the remaining possibilities for us to actually explore this. So if we sum this together, we have, this is 18 plus 9, that's 27, I think. And then 12 plus 96 gives us looks like 108. Yeah, so the possible summation of values that we can actually get are these ones. Let me just circle them with a different color. You can get this 27. You can get this. You can get 36. You can get 99. You can get 18. And remember, the original number we started with was 36. Is there 36 here? Yes, we do have 36 here. So this is 1, and then that means that 36 is a valid number that we can use. Do we get? So now this is what we need to do, and we can see that this is basically at every point we are making a decision to either divide or not divide. So at every point we have two decisions, divide or not, and we do that up to the length of the entire string, up to the length of 4. So the time complexity of this approach is equal to what? 2 raised to the power the length of n. You will see, so 2 raised to the power the number of digits within n, actually. So 2 raised to the power the number of digits, not n. So this is going to be 2 raised to the power the number of digits in n. Now the number of digits in n is what? Number of digits. So if this is like the number we are looking for, what are the number of digits within 1 to 96? I mean, if you think about it, what are the digits, number of digits here? Say in mathematical way for us to represent it. Yeah, actually there is. There is. So if you imagine that these are like base 10, these are decimal numbers, these are base 10 numbers. At every point we can just say that, okay, the value 10, log of 10 is 1, log of 0, I don't even know what that is, but log of 10 is 1, log to base 10, so log to base 10 of 10 is 1, so for 100 is 2, for 1000 is 3. Yeah, so we can see the depth of this tree is up to 1, 2, 3, 4. Yeah, so at 1000 the depth is 3, but I mean it gets, because it's a little bit more than 1000, this is 4. Yeah, but for all intents and purposes we could actually just say, okay, this is roughly log to base 10 of a number plus 1. Yeah, so at the end of the day, this is actually just log to log 10 to base n. So in terms of time complexity, this problem, this approach is solving this time complexity for this particular algorithm that we just created is 2 raised to power the number of the depth of this tree, and depth of this tree we've evaluated it to be log to base 10 of n. So this is going to now be 2 raised to power log to base 10 of n. This is the time complexity of the solution. The space complexity is going to be the depth of this recursion tree, and for that, space is going to be, so let's not forget this is big O. You see, so so let me just make it a little bit clearer, because this might not be the clearest way I can do it. So the time is big O of 2 raised to power log base 10 of n. So this is log to base 10, and then space is equal to O of log to base 10 of none. Yeah, so this is it. Is this efficient? Can we do better than this? Actually, right now it's a little bit difficult to say that, but let's see if it's possible for us to do better. We can, so basically we are doing an exhaustive search here. We can sort of find a way to prune this search, to know when to not bother even checking anymore. And we can check that. We can see here that when we have a 1, we had this value to say that we had this value to like a counting sum, and we pass that sum down. Then we have a 2, we add the value to the to the counting sum to pass the sum down. We have a 9, we have a value to the counting sum, we pass the sum down. We have a we have a 6, we add the value to the counting sum, we pass it down. So at every point when we are taking up chunks, we're adding that value to a sum. When we eventually take up a chunk that is too large, say say this particular case of 1296, that is pretty large. If we take up this chunk and then realize that we have a sum that is that is larger than the original sum, there's no need for us to further continue to check. Let's say, for example, now we are in this case where we end up in 129. So in this case, there's no need to further explore, because definitely no matter how many numbers is here, it will never give us the original 36, because 129 is already greater than 26. Yeah, so that's the way we can prune the search. That's one. But can we still do better than that? Well, maybe we can do better. If you think about a situation whereby we have, let me see. Think about a situation whereby we have, okay, yes, so we have a good example. So think about a situation whereby we have, we have some arbitrary numbers. We have a number that starts with, let's say, okay, you're wrong. So let's say we have like 1, 1, 1, and then some other bunch of numbers, 2, 3, 4. So at some point in this division, we could be in a situation where we've explored up to this index. And in that case, we have in that scenario, we could have a situation whereby we have splitted, we've taken the first integer, and then we've also taken 1, 1. But let's say we've taken the first one, then we take 2, and then we are now exploring from this index down. And let's say we are also in another situation. So this is one case. We are here to explore, the remaining numbers here. This is one case. And now say we have another case whereby let's say we took the first 2 digits, so we have 11, and then we take the next one. Then we have this left, all of this left explore, 2, 3, 4 left explore. If you check out this sum, if you sum 1 and 11, we have that stuff. Same way if you sum this 11 and 1, that stuff. So it seems that regardless of how we got this value of 12 at this particular index here, if we have calculated for this, there's no need for us to explore all of this anymore, especially if we've calculated for this and we have a value that is false. There's no need to check anymore, isn't it? Yes, because whatever it is that we can get from here that gives us a sum, no matter how we want to divide it, if there is no way for us to possibly combine it and get the original number, let's say the original number is a 47, if there's no way for us to combine, then there is definitely no way for us to combine this also. So that rings a bell, isn't it? So this is suggesting to us that, okay, in addition to this our exhaustive search approach, it seems that we can use some form of dynamic programming. So with this, we can introduce memoization. Memoization will help us here in such a way that we could memorize based off of the index and the original sum. So we can see that here I said that if there's a way we could get 12, up to this index, then there's no need to check the other ones if you explored it before. So you're going to memorize based off of the value here and that index. Do we get that? The other thing is, it's important for us to memorize based off of this sum and the index, not just the index, because if you think about the possibility whereby we took, like as a first chunk, we took 1, 1, 1. So we took 1, 1, 1 as 111 as an initial chunk. It doesn't mean, so 111 as an initial chunk is a different part from this. The total sum there will be different from what we get from this original one. Do you get the idea? Yeah, so that's why we need to memorize based off of this sum and this. So with all these things I've said now, that will mean that we can reduce this time complexity from what it is initially, which was exponential, 2 raised to the power, log, 2 raised to the power logarithm, all the way to a polynomial problem that will be dependent on what the sum can be and the index I, or the index in the value. And then in worst case, this sum, remember, we are going to try to make sure that we are still going to prune. So we can get a worst case whereby the sum will never go beyond the original sum of the number, which technically is log of, which technically is going to be the log of the entire length. The sum. In the worst case, we're going to be thinking about log of the entire length of the value, or rather, maximum sum can go up to is actually the value n. So the maximum the sum can go up to is the value n. So let me just, so the maximum the sum can go up to is the value n, and then the maximum that the sum can go up to is value n, and the maximum that index can go up to is the entire length of the value, so which we have evaluated before to be the log of n to be log of n to base 10. Yeah, so log of n to base 10 times this value of sum. And actually, I'm trying to evaluate what this sum can be, but we've seen that we do not need to actually evaluate the entire sum. We can prune it, isn't it? We can stop the search, halfway along and not evaluate the rest. So basically, this will be lesser than actually what it is. So this is a solution with dynamic programming, and then we can now attempt to solve this. Actually probably will need to review. I think let's take a moment to think about these parts of this time complexity analysis. This sum can get to a maximum value. Yeah, actually, so the sum can get to the maximum value of the inputs, and the maximum value of these inputs can be actually, yeah, so this is seems to me that this is actually roughly something like log maximum it can be maximum it can be for every input is rough. Yeah, so so this is, it seems to me that this is roughly log n to base 10. Yes, so basically, so the time complexity analysis of this particular approach that we've come up with now is we reduce this problem from being a log rhythmic, from being a 2 raised to the power log exponential solution into one that is going to be using log of something, roughly something in this range, log of n to base 10 times log of n to base 10. Reduce this to this, and then in addition to this would then go all the way. So this is the complexity of the subroutine, and then we loop all the way from initial number to the end. So now let's go back to the initial problem. So now we've come up with a solution, and a sort of efficient solution for checking this. So the time complexity of just this part of this algorithm is going to be of we see log n and log n. So we created a solution for this that gives us this. So now here's what we have, and then the overall time complexity will then be the initial n, because we're going to loop through all of them one by one, and then for all of them looping through, we are going to square it, and then we're going to run this. So this is actually roughly n squared, and if we do that together, that would be 2 times log n, 2 times log n. So at the end of the day, that's still log n. So log n times log n. So the overall time complexity for this solution is of log n times log n. So that would be n times log n times log n. This is the overall time complexity for this program. Apologies that this is getting a bit long, but I believe this understanding of the approach is what is much more important. So now we can now attempt to solve this. And so for those of you that still want to solve this, we can be here together and then attempt to solve this using the idea that we've come up with. So what do we do? So the first thing is, because we want to solve, so to solve this, it means that we need to be creating substrings, isn't it? So we are going to go from, say that we go from we're going to create a subroutine that will do this. So let's have a subroutine that does this, and then we're going to call it dp. We're going to have the index, we're going to have this sum, we're going to have the index, we're going to have the sum, and then we're going to have a let's say so let's say we have like the number represented as a string, and then let's say we now have the target number we are trying to form. You get the idea? So from what we've said, we're going to loop from We're going to look from I is equal to 0. So index is equal to 0, index is less than, we're going to look from index, index is equal to 0. Initially I will be 0. So I'm going to look from index is equal to I, all the way to index is less than this string numbers length. Then once we do that, then we would increment index. So now once we do this, we're going to take a chunk from the index position. So we're going to have a, so let's call it like a left. So the left would be so this string we're going to perform a substring. We're going to take a substring starting from index I, if you remember, all the way to this value of index that we have plus 1, so that we can take it. So imagine in this case where I is 0 and then we're starting index at 0, and then we're going to take have to increment the index position so that we can take that chunk. Then index goes to 1, then we can take 2 chunks. Do we get? So this is what we have. Yeah, so this is right. Now the left, this is left, the right part will now be this, the right part will be the string number dot substring, and this will be from index plus 1 all the way to the very end. Do we get? Now the left part is sort of the part that we kind of care about right now. So what we just need to now do is that we are going to find the value, and then we're going to do that by converting the value to an integer. So we're going to pass int the left. So once we do that, we would recursively call the function. So we say, let's say we have like a boolean, let's call it valid. So it's being valid will mean that we're going to recursively call this. We are going to recursively call this. We are going to call it for the next index. So the next index of this value is the value of index plus 1. You remember that's where we're going to start our dividing from. And then the sum is going to now include the value that's this value, the value that we calculated here from the left, and then we will pass in the same string number which will not change, and then the target is going to remain the target. This is basically what we're going to do. Now we will repeat this for every other possibilities. Yes, but however, if we get, so this is where the pruning comes in. Once we get a value that is valid, once we get a value that is valid, if it is valid, we immediately return true. You don't even need to exhaustively search for the remaining ones anymore. Sorry, this is true. We return true. But in other case, if it happens that we exhaustively search and then we do not find, then return false. That's technically not possible. Yeah, so this is basically the entire exhaustive search that I spoke about earlier. And then that's this part of this approach, exhaustive search, breaking everything down. Then in addition to this exhaustive search, we then introduce the pruning. So with this pruning, we immediately check if it's valid. Once it's valid, return true. And then you can imagine that will happen recursively. Once we get to a point where it's valid, we just return true. So what does the validity actually mean? So the validity actually means that if we get to a point where we have where the sum is equal to the target, in this case we just return true. But otherwise, even if if you get to a point where the sum is equal to target, and so this is very important, we have gotten an I has gotten to, that is the index I has gotten to the point where it's at the very end of this string norms length. So that is, we have included all the possible substrings. If we do get to this point, then we need to return true. So that is when we return true all of this point, and then we check if it's valid. Once it's valid, we return true too. Do we see? So this is actually the solution to the problem with the pruning. The pruning is this step where we immediately check if it's valid. Once it's valid, we return true. But then there's some extra pruning that I also mentioned. That, all right, aside from this case where it's valid, what if we get to a case where the sum just becomes larger than target? If you get to this case where the sum is larger than target, then it's technically not possible to to find this number. What do? Return false, because there's no point. If we still need to divide and then sum is already greater than target, then there's no way to do it. Just return false. This is another pruning. So, and then this particular pruning relates to this point. We get to a particular division that is already greater than, the value is already greater than what the sum is already greater than what we originally have, which is the 36. Or is it somewhere? In that case, then there is no need to continue to search. You just return false. There's no need to continue to split out the remaining part of the number. So these are the two pruning steps. But then in addition to this, we can do more. Yes, so if you want to call this function now, what we just do is we just say, okay, we're going to return dp, starting from index 0 with an initial sum of 0, and then with this value squared. This is the number we want to split, but we need to pass it as a string. So one easy way to just do it is just to have a string and then do this. This is adding an empty string to a number. Then the target is this. So once we do this, this is definitely going to work. Is you just split it in all possible ways and then give us our value if it exists. So this is the entire solution to the problem. We are going, and then we'll return back that value. We check sum. Remember, we are adding the squared to the sum. Return the sum, and then once we are done, that sum is what we return. So let's see. So if you haven't missed anything, this should work fine. Before we go ahead to introduce memorization steps, so let's just see. Yeah, so as you can see, this is accepted. This is green. This works. 1 time 1 millisecond. Actually, this might not get accepted if you attempt to submit this. But let's see if it gets accepted. Oh, actually, it gets accepted. That's interesting. It gets accepted. However, according to what I've said since, we can do better than what we have actually done right now. We can introduce a memorization step, especially on this sum and the index I. So what do we do to introduce memorization? Yeah, so if you guys if you guys sort of know me, I usually talk about memorization this way. I would say that you want to so first of all, we want to have like a key value based data structure that allows us to quickly check if we've evaluated a particular state before, and then if we have, we just return back that particular value from the calculation. So what happens is that in this case, we would create a data structure that is going to be so we create a data structure that is going to be a map of let's just use a map of string right now, and to okay, let's use a map of string to boolean. Yes, we're going to call it a memo, and it will be a hash map. Now that we have this memo, for each state, we're going to have a sort of a computation for the memo of that state. Yes, so this memoization is going to, remember, the memoization is done based off of the level of each of these squared. Remember, so we are doing memoization based off of the squared. That means that we are memoization index splitting for 81 is different from index splitting for 100. Same way that's different from index splitting for 1296. So what we do is that we need to actually have, this is the wrong place for this to be. It should actually be here. Remember, for every squared, that is where we have this memo. Now at this point, we need to take this memo, and then a new memoization table sort of we need to be created for every evaluation. So we pass this down into this function call. That will mean that we need to adjust this function call to now have this parameter memo. And that also means that we need to pass this memo down, and that means that we need to adjust this also to have the memo. So now that we have this, all that we need to now do is, at this point we just need to now check, we sort of like, we need to create a key. So one easy way to do it is, remember, we are memoizing based off of the sum and the index I. So we create a key with I. This is one very easy way to do it. Key with I, and then concatenate that with the sum. This is going to be our key. Now that we have the key defined, we just check, if this our memo contains this key. Then return memo.get for the key. But in this other case, whereby it doesn't work, we get a value of false. What we just simply do is we need to memorize this value actually. So we need to put into the map the same key with the value of false. Do we get? So with this, it's the same problem, the same solution, just that we've added a step of memoization on top. We've added this check, and then we've added this check. Mind you, we guys need to realize that this memoization actually is for the false case, the case where there's no need for us to explore. Putting in mind that once you find a value of true, we already have the pruning step. Once we find a value of true, we no longer explore the other parts anymore. We know that there's an answer, we just return. So let's see if this is any bit faster than what we've done. Okay, so I think I've missed out something. I just said, okay, yeah, so I need to pass the memo. Obviously I need to pass it down here. Just missed that out, but aside from that, yeah, you can see it works. So let's see if it's a little bit more efficient than what we already have. Actually, it seems that the memoization step is making us perform more operations than we should. Yeah, but that is how memoization is supposed to help. All right, guys, thank you very much for coming around. We hope to do this another time. Bye, guys.